the KU Community Webinar Series. I'm joined by Dr. Igor Boiko. We're going to be talking about your book, and I feel like the best place to start would be a basic overview of controller design and what it's used for.
Okay, thank you very much for this introduction. It's my pleasure to be here. Because this talk is probably intended just for general audience, I would like maybe to say also some general words about the control systems design and what it is about. Control system is usually can usually be described as a feedback control system. For example, if I would like to take this book and place it back in its place, I initialize or I activate my control system, which consists of my eyes, my brain, my muscles, to put it, and to put it precisely on the top of this stack. I actually can see with my eyes, and it provides me the feedback to put it precisely in its place. And my brain acts in this sense as a controller. As a controller, so which implements or which works in accordance with a certain algorithm. The control theory deals with these dynamic systems and control algorithms that allow us to do certain things similar to that one by automatic control systems. And it has a very, let's say, rigorous mathematical theory behind it. It's based on, let's say, classical mathematics, and lots of mathematicians were involved in control theory and has been involved, now are involved. So it's a mixture of mathematics, a blend of mathematics and engineering. So that's where they come together to produce sometimes wonderful results, and we can see that these results in applications everywhere, in aerospace, in biomedical engineering, our everyday life, and so we can see them. So, and basically control is what I have been doing all my life. So I worked on maybe last a little bit over than 10 years. I have been working on one direction in the control theory, which is represented in this book. It's called non-parametric PID controller tuning, but it's more general than only PID controller tuning. It can be applied to all controllers, but mostly to these type of controllers, which are called PID: proportional, integral, derivative. PID stands for proportional. Proportional, integral, and derivative. So when I was illustrating my action, how I was put in this book, and I said that my eyes can precisely, let's say, together with the rest of the brain and body, allow me to precisely put this book on the top of this stack.
The eyes are telling you.
The eyes are telling me where the, I would say, what we call in control theory, where the error is. The error is the difference between the desired position of this book, which would be here, and the actual position. If I put it here, I see that this difference is that distance, for example. And if we have a proportional controller acts proportionally in a proportional manner with respect to this distance, trying to eliminate it. So the action of the control is proportional to this error.
So what you're doing is turning something that's very natural for us if I pick up a book and put it down, I can pretty much get it down without thinking about it. And you've got to put that into a system to make it do what humans find very natural.
Yes, it's not me who invented that. It's been known for like
In general,
just not centuries, but dozens of years, definitely. So, and this is the basic control. Proportional control is the basic control.
Okay.
So, if we would like to make it working better, so for example, we can put we can add integral component, which will be also looking at to the integral of this distance, and a derivative control, which will be looking at the derivative of this distance as a function of time, because it changes with time.
So it's all ways of making it more accurate.
Proportional control only would not allow me to eliminate this difference completely. So if I use only proportional control, it would stop somewhere here. So the let's say result of my action, the integral component of the control would allow me to put it precisely to its place. And the derivative component would result in a more stable, I would say, motion or more stable work of the system. So together they are like nice ingredients in this control. But to blend them together, these ingredients, they must be blended in a very precise, let's say, proportions. So that's what tuning is about, and basically a control system is also about that. But there is a difference between tuning and control. Actually, control usually assumes that we start designing the system like from scratch and do it in using the mathematical models and proceed to the end design, to the final design, including the selection of the type of the control, the structure of the control, the parameters, parameter values of the controller. Tuning usually means that we, for example, implemented the control already with some maybe arbitrary values of the parameters that are not non-precise. It's like tuning of a guitar, for example. The strings are there, but you cannot play it until you tune every string perfectly to the necessary tone. Same thing is here. So the control is there, but the system cannot work until you tune these parameters of the controller to the necessary values. And here where tuning comes. So is let's say is a certain procedure and certain area in the control discipline. It is very practical. It is very practical, definitely, and I hope to demonstrate some videos where it is used in various areas of engineering. So maybe the most impressive would be the tuning of UAVs, and this is what.
That's where it sounds like it's quite useful. If you've got a UAV, an unmanned aerial vehicle, a drone as we know them, and you've got one flying through the air, sometimes if something gets in the way or there's a gust of wind, they get very jaunty and kind of fly like this. And I suppose you can think of that as your initial control design. You've made something that flies, but it's not particularly smooth, and adding in the tuning makes it nice and steady.
Yes, you know, actually just to make it fly, you need a pretty good tuning.
Okay.
Pretty good tuning already. Without it, it just cannot fly. It will flip over or it will hit the wall. And in fact, it happens, and it happened to us. So it's when we did this, started this work with the with UAVs, with drones in the room. So we had quite a number of those incidents. So when we it flips or hits the ceiling, breaks everything. So I mean, breaks the propellers, and so we need to falls apart. Even falls apart. We need to let's say put all the parts together and reassemble it. And that's why we were very, very let's say careful about tuning, about implementing these experiments because of the cost of this bad outcome if it happens, bad outcome. And I hope to demonstrate it. So it was actually the very first tuning that we applied to a drone, automatic tuning that we applied to a drone, and which was really successful. And there were two people, my student and I. We were very just surprised, pleasantly surprised, how well it works. We didn't expect that, because we spent a month, literally a month, doing the manual tuning of this quadrotor, crashed it a few times trying to change the parameters, and came to like certain result which was like satisfactory result. And then we applied this, we were supposed to do that, but we had to have certain benchmark first, and try to see where it is supposed to be according to what we could do. And so that the values that auto-tuning provides would not be very extremely different from what we were able to obtain manually. But they were.
They were?
They were.
Okay.
Yes, they were. And that was a kind of surprise for us, and we were very cautious about whether we should implement them or not, because we may have just another crash.
Yeah.
Suddenly, so we decided, let's try it anyway. So if worst comes to worst, we will crash it. And suddenly, what happened? It worked just perfectly. And we spent a month and were not able to come even close to the results that the automatic tuning, which is described in this book that I wrote.
This automatic tuning, this is where it's correcting itself.
Yes. Okay. It's auto-tuning, but it can be implemented at that time. It was not fully automatic.
Yeah.
It did the test. It provided us the parameters, and we saw the parameters. We just checked them what they are, and we manually entered these parameters. Just programmed them. But yes, right now it's proved. This technology proved, and we implemented in the automatic manner. And right now, actually, there is a team in QCARS. QCARS stands for Khalifa University Center for Autonomous Robotics, QCARS, or Autonomous Robotic Systems, QCARS. And there is a group there. It's actually, the team is led by Dr. Yahya from the Aerospace Engineering Department, but what the control activities or activities related to control systems, so I covered that part. And so many technologies, almost everything, let's say to some degree, involves the tests and the tuning methodology that I developed previously and developed later with my students, and so it works like this. And I think I consider that, and that's true, the technology which is developed within KU, I would say the technology is very successful. The technology is very successful, and not only in UAVs. So I have other projects and or had some of them in process control. That's where it worked just perfectly, absolutely. Even in power electronics, and the tuning happens of the power electronic system happens. Your guess, how long does it take to tune?
Manually or automatically?
Automatically.
Seconds.
No, 10 milliseconds.
Wow. 10
milliseconds. So it's less than a blink of an eye. Everything is done. Yes, it's that's how it is done. Not, of course, not in UAVs. In UAVs, you need a few seconds, and then it is tuned. But in power electronics, it's 10 milliseconds.
That's instantaneous, practically.
Yeah, it's instantaneously, and not noticed to the, let's say, equipment which is connected. It's live. It's done live. So it's when the equipment is connected or the power converters are connected to a grid, or it's still in the process. The project is not complete, so we are trying to expand it. So we have the DC to DC converters, DC to AC converters. So we are now trying to work with the AC to AC converters. So it's like a continuation of this, but at least it is proven that some types of this equipment, and it works fine.
And sure, I mean, the projects may still be underway, but it sounds like there are a lot of industrial and practical applications for this.
But it also that's what I would like to say. It is also an involvement of a lot of mathematics. It's very complex math which is involved in it, because we need to deal with physical objects. Of course, physics also, depending on what we are considering. It's the power systems, and it's electricity, and all that, plus mechanical motion usually. In drones, it's mechanical motion, then aerodynamics, and all that stuff. So process control, also flow of fluids, thermodynamics, and all that. Plus lots of mathematics, especially such things as, so we actually had to deal with such an area as the very complex area, which is I can refer to as optimization on the uncertainty. Optimization on the uncertainty. And this is not, even virtual optimization is quite complex, but optimization on the uncertainty is a different level. And that's where actually I came up with even some new mathematical approaches in this area in general. And they apparently are let's say successful in practice, and that's we have the results, and we are just keep let's say keep working in this area. We keep producing new results, and it's in my opinion, it's quite successful.
Yeah, that's quite the achievement.
What else can I say? The basics of maybe I should emphasize the fact that this is a non-parametric tuning.
And when you say non-parametric, does that mean the bits that you can't predict, the uncertainty? Is that where that comes in?
The non-parametric is, there are two methods of controlled tuning. See, that are called parametric and non-parametric.
Makes sense.
Parametric is where we are trying to, where we, first of all, in both of them, we run a test over the object that we are trying to, the system that we are trying to tune, or object we're trying to identify, and parametric methods are based on the test leading to the development of a mathematical model of this object. A mathematical object of this model. So we have like three entities in parametric tuning: the actual object, then the mapping into the mathematical model, into parameters of the mathematical model, and once we obtain that, we apply normal design procedures that we use for theoretical design. So we're assuming that the dynamics or physics of our object is given by this model, and we can deal with this model precisely. Let's say this model is precise, and we can design our control based on this model, and our result will also be precise.
Okay.
In non-parametric tuning, we are trying to produce mapping directly. It's two entities from an object through test on an object to the controller tuning.
Okay.
To the controller tuning, without having this intermediate entity, which is the mathematical model or identification of mathematical model of this particular system. So where's the weakness of the parametric tuning? So we cannot describe mathematically the system. Usually we cannot describe it to the necessary precision. So it's models. We can use one model or another model, so they are still models. There is a saying actually about models, that all models are wrong, but some are useful. So, yeah, they all are wrong. So we can try to use first order model, second order model, third order model, fourth order model. So the higher the model, the potentially can be more precise, more accurate. But there are lots of, I would say, obstacles on this way to identify higher order models. So that's why usually like pretty low order models are used. They are considered good enough to let's say to design a controller. But once the controller is designed, we see, okay, there is still a mismatch. There is discrepancy between. So and it can be tuned better. So it's, what is proposed here? I should also mention that the overall the idea of non-parametric tuning is an old idea. It's known. It comes from the works by Ziegler and Nichols. It goes back to 1942 when they proposed the non-parametric tuning. So in non-parametric tuning, there is a mapping directly from the test to the controller parameters, but at the time of Ziegler-Nichols, it wasn't the idea of precision. It wasn't the idea of precision. It was maybe not quite precise, the tuning. The idea was the simplicity. So the advantage over other methods was the simplicity of this tuning. So what I proposed here, which is described in this book, is to, and Ziegler and Nichols developed all these as a general approach for all possible systems in process control, for flow loops, pressure loops, level loops, temperature loops, for all those objects. And they are also used for, even now, for other, let's say, types of systems. What I propose is to narrow the classes, to single out classes of the systems for which we can develop the non-parametric tuning rules. But develop these tuning rules, develop these mappings between the test results and the object and the controller tuning parameters very precisely. So, and this is now mathematics is put into that as a foundation of this, which comes to, so the problem is formulated as optimization under uncertainty. Why uncertainty? Because we don't know what particular system we are going to test and design a controller for. So whether it's going to be this small, let's say, quadrotor, or this huge one, it must be, but at least we know that this is going to be a quadrotor or multi-rotor at a certain VV. So this is the class that we describe. And for the class, we can develop this mapping, and the mathematics is developed for that, how to produce this mapping from the results of the test to the controller parameters. So under the uncertainty that we don't know to which object we are going to apply this mapping. So and the mapping itself is a certain function. So we need to design a certain optimal function, I would say. So the whole idea of the designing of these optimal non-parametric tuning rules, it's a design of an optimal function for a certain specific class of objects.
So that you can have a class of objects and you can put your technique on pretty much anything, as long as you know what
Yes, but right. For example, here in this book, I started with process control. It was, it is written, I think, in 2013. At that time, I was working with process control systems, and here I was developing the tuning rules for flow loops, pressure loops, level loops, temperature loops, and so each type of these loops or each type of these processes is a class. So, for example, we have separate tuning rules for flow loops, separate tuning rules for pressure loops, and so on. Because we know what we're tuning, whether it's a pressure or flow. So it's not a problem. It's not like an unknown.
There's no uncertainty there.
No uncertainty here. But the uncertainty is what the dynamics of this would be, of this process. Maybe I should say a couple of words about because there are 3 books here, and this is the book on discontinuous control systems, which maybe it's a mathematical theory, but it is relevant to what is given in this book, because the test that is used for this tuning, it's called, there is a subtitle here, a modified relay feedback test. So this test, which I propose for this, is extremely important. It turned out to be, I would rather say, extremely useful for the tuning, and it is based on the theory of these discontinuous control systems, which relay systems are. And this is in the videos, which I hope to show you. You will see that there is the test result in the oscillations of the objects. For example, oscillations of the UAVs in their channels, pitch, roll, yaws, and for example, it's like this. And another book which was written together with my co-authors, Luis Ravillard, Leonid Friedman, and Rafael Eriarte. So it's self-oscillations in dynamic systems. So again, all these are related. They cover different aspects of the control theory, but of course they are related because all of them are related to oscillations to some degree. So.
Excellent, Dr. Igor, thank you so much for joining us.
Thank you.